안녕하세요. 오늘 반갑습니다. 오늘 수업에 참석해 주셔서 고맙습니다. In the last class, I was talking about the basic theory of differential signaling. You may remember that in differential signaling, we are having three method systems, and you remember that in the single-end transmission line, we have two method systems, ground and signal line. But in differential signaling scheme, we're gonna use three method systems. And to take advantage of a symmetry, we're gonna use odd mode excitation and even mode excitation. In odd mode excitation, you remember that we're gonna have plus voltage wave will be applied to the one metal and minus voltage will be applied to the adjacent metal. And because of that, we're gonna have a virtual ground plane. Because of this virtual ground plane, we will have very good impedance matching during the transition of disconnection from chip to package, package to PCB, and PCB to cables. So it is much easier to maintain impedance. Another advantage of this differential signaling scheme is that because of this virtual ground plane, we have ground plane and we have opposite voltage and current, so EMI radiation will be canceled out each other. One disadvantage of this differential signaling scheme is because we're gonna have two signal methods on the top of ground. In the common mode and even mode excitation case, we're gonna have same polarity of voltage and current, and it will propagate at the speed of light. And usually common mode is very problem, and it will take a lot of EMI issues because of common mode and because both metal is carrying the same current and voltage, and it will produce the EMI. And also in the previous class, we was talking about odd mode impedance and even mode impedance because field distributions are different, so impedance will be different. In the middle of even an odd mode impedance, we're gonna have single line impedance, and phase velocity of odd mode and even mode will be different. So when you are designing the differential mode interconnection, we have to control these impedances and propagation velocities. And now today, I would like to talk about excitation and propagation and deflection of differential mode and common mode. So in order to take advantage of this differential signaling scheme, we have to design the voltage waveforms and the timing margins and something like that. So in order to do that, we have to control the excitation, propagation, and deflections. To control that, we have to design the terminations. These are the subject of the class today. First, let's start the excitation of differential mode. I will assume that we have odd mode impedance of this transmission line, and we are assuming that at the end of transmission line, we're gonna put termination resistor RD, which is the same as odd mode impedance. You may remember that we're gonna have a virtual ground plane. So a termination impedance RD is connected between one line to the virtual ground. Actually, virtual ground and real ground is connected. In single end termination case, we were terminating this line with the single line impedance, characteristic impedance. But in order to avoid any deflections at the end of transmission line with differential mode excitation, we have to terminate this termination with odd mode impedance. You remember that even mode impedance is larger than 50 ohm and odd mode impedance smaller than 50 ohm. That means when you are exciting your transmission line with differential mode, your termination should be odd mode impedance. By mistake, if you put characteristic line impedance, single line impedance 50 ohm, differential mode will be deflected. But anyway, if we terminate the line, differential line with odd mode impedance, differential mode will, the reflection coefficient is gonna be 0. That means we will avoid any reflections. Then time delay between transmitter to receiver will be totally determined by the length of this line, and delay will be determined by length of the line and odd mode of phase velocity. You remember that even odd mode velocity is faster than even mode. That means if we are exciting differential mode and common mode together, usually differential mode arrive earlier than even mode. That is quite an interesting thing, and that will usually creating phi in the crosstalk. And we're gonna cover it a couple of weeks later. And then we're gonna produce voltage wave. This is actually an odd mode voltage wave. We are assuming that at one line we are exciting with a positive voltage, and in the adjacent line that is labeled, this line is labeled P and this line is labeled N. We're gonna excite adjacent line with negative voltage step. This is a differential mode excitation. So when you are designing differential mode interconnections to minimize the impedance discontinuities and EMI, you have to excite a differential mode and odd mode like that. One line has to switch it to 0 to voltage, positive voltage level. In the adjacent line, you have to excite from 0 to minus voltage step. And this voltage step, it will be determined by step voltage divided by ohmic ratio between odd mode impedance and source impedance. We are assuming that is odd mode impedance as well, and odd mode impedance. Let's assume RD is 50 ohm, odd mode is 50 ohm, and odd mode is 50 ohm. It's gonna be half voltage. So this is a special case where we have source impedance is matched to odd mode impedance, and termination is matched to odd mode impedance. And then we are exciting the transmission differential mode. Then half voltage wave will propagate along a top metal to virtual ground plane, and another minus voltage will propagate along the line between virtual ground plane to minus metal. And that the amount of that wave is gonna be half V. Why is that? Because source impedance is matched to odd mode impedance and termination is matched to odd mode impedance. So in the P line, we're gonna have positive wave will propagate at the speed of light, And on the negative line N, we're gonna have minus voltage, step voltage will propagate at the speed of light. And in this case, we're gonna have current will be induced at the top metal and virtual ground plane, and that amount of current wave will be determined by voltage wave divided by odd mode impedance. And if we rearrange that, that is determined, will be related to voltage divided by differential mode impedance. Differential mode impedance is, you remember that it is twice of odd mode impedance. Image current at the bottom metal will have a minus sign, and also it will propagate in the g direction at the speed of light. In this special case, time delay between transmitter and receiver will be determined by length of interconnection divided by phase velocity. And yeah, odd mode phase velocity. So it is not difficult subject, but this is a very special case, but it is good to think about how to excite differential mode. I'd like to summarize this slide. Number one, how to excite it. Number one is one line has to have a positive step pulse, and the adjacent line has to have negative step. Then we are going to excite differential mode. To minimize the reflections at the transmitter and receiver, we're gonna terminate at the receiver with odd mode impedance. Also, we're gonna terminate source impedance with the odd mode impedance. That is distinctively different from the single end case. And you remember that this odd mode impedance is an impedance between the virtual ground plane to the metal. And then by the ratio of impedance between source resistance and odd mode impedance, half voltage wave will generate and it will propagate into the receiver end. And the current wave, amount of wave will be calculated by dividing the voltage wave with odd mode impedance. That is definition of impedance. And the time delay between transmitter and receiver will be determined by the length of interconnection divided by odd mode phase velocity. You remember that odd mode phase velocity is the faster than single mode case, and this is the single and the transmission line, so it will move a little bit faster. This is a summary of differential mode excitation. Chang Seon, are you there? Can I speak to you? Okay. No, 조세영, are you there?
네, 교수님.
Would you summarize the excitation of differential mode to us?
네, 좀 부족하겠지만 간략하게 설명을 한다면 일단 디퍼런셜 모드 같은 경우에는 두 개의 라인 사이에 버추얼 그라운드가 있어서 그 리플렉티브한 요소 때문에 일단 상이 반대인 두 개의 웨이브가 간다라고 가정을 할 수가 있게 되고,
네.
그로 인해서 이제 입력되는 것 대비 반절의 웨이브가 지나간다라고 가정을 할 수가 있게 되고요.
네.
그리고 만약에 터미네이션 관점에서는 소스 임피던스와 트랜스미션 라인의 특성 임피던스 그리고 로드 임피던스가 같은 조건으로 동일하게 터미네이션이 된다라고 한다면 지금 주어진 수식과 같이
네, 맞습니다. 그래서 여기 독특한 거는 소스 임피던스와 터미네이션 임피던스가 반사가 없게 하려면 오드 모드 임피던스로 매칭을 해야 된다는 거예요. 그죠? 그냥 우리가 엔지니어들이 별 생각 없이 55옴 라인을 두 개 갖다 붙이고 디퍼런셜 모드 만들면 오드 모드 임피던스가 생기기 때문에 그냥 터미네이션을 55옴으로 하면 반사가 생긴다. 이런 거 하나 하고요. 그리고 디퍼런셜 모드가 싱글 엔드 라인이 1나노세컨드 걸렸다 그러면 오드 모드는 950 피코세컨드 먼저 도착해요. 도착 시간, 필드 디스트리뷰션이 다르다 보니까 디퍼런셜 모드로 익사이테이션 하느냐, 싱글 엔드로 하느냐, 커먼 모드 하느냐 다 도착 속도가 달라진다. 이 말씀을 드리겠습니다. Thank you. So once again, this is another summary of differential mode excitation. In the graph, as shown in the previous class, we have length of interconnection is L. We have odd mode and even mode, and I am assuming that source impedance is terminated with odd impedance, and the receiving end termination is terminated with the odd mode impedance. And then because of that, reflection coefficient is becoming 0. Now, in the time domain waveform, when they are switching, P line will be excited with positive voltage, and the N line will be excited with a negative voltage. So this is wave, and this is wave. So if I draw the wave's excitation in the time domain graph, this blue line is actually corresponding to common mode. I'm not going to talk about the common mode excitation at this moment. And at this moment, we are assuming that common mode is a constant DC voltage. This is usually what we are having, because if there is any fluctuations of common mode, it will radiate and it will be a source of EMI. So when we are designing the differential mode interconnection scheme, we both have common mode and differential mode, but we wanna make common mode. We wanna make common mode that actually is a free reference as DC as possible. So if there is any noise, that is what we don't want that. But next class, I'm going to talk about when we are generating the common mode. But at this moment of analysis, and I'm assuming that common mode is a DC voltage. So when we are designing a differential mode scheme, we have to design a common mode as well as differential mode. But at this specific case, I'm assuming that common mode is DC level. And then wave property is only coming from differential mode. So when so this DC common mode is becoming actually virtual ground plane. DC, when we are exciting wave, they don't care about DC level. So this actually for reference level is becoming virtual ground. And we are generating delta wave on the P line, and it will propagate as a speed of light. And on the other line, we're gonna generate the negative pulse, and it's gonna have opposite polarity. And because of that, we're gonna maintain the reference plane. And at a time delay, it will reach to the receiver end VB. And you remember that will be determined by length of interconnection divided by odd mode phase velocity. And please remember that this is shorter than even mode of phase delay. So odd mode, differential mode delay is shorter than the common mode delay. That is causing a lot of problem. So whether you are exciting your lines with a single mode or differential mode or common mode, arriving time will be different. So this is another way of explanation of differential mode excitation. Let's assume some interesting case. Let's assume we have odd mode impedance 45 ohm. By a mistake, let's assume that you put source impedance 50 ohm and termination is 50 ohm. One problem associated with this special case is that then reflection coefficient odd wave will be reflected at the receiver end, and also at the source end we're gonna have odd mode reflection coefficient. Then because of that impedance mismatching, there will be multiple reflections. In most cases of high-speed interconnections, we want to avoid multiple reflections. So we gotta be carefully design odd mode impedance. And that should be 50 ohm. But by a mistake, if you have odd mode impedance is 45 ohm and source impedance is 50 ohm, by the ohmic ratio between source impedance and the odd mode impedance, actually voltage wave will be less than half voltage. That is gonna be on basically the voltage wave will be determined by the ratio of source impedance and odd mode impedance. Because odd mode impedance is smaller than 50, we're gonna have less step voltage compared to impedance matching case. Now, let's move on to our next subject to talk about excitation of common mode. In order to excite common mode, both line has to have step input. By switching some transistors and by connecting the power supply, you have to apply the both same polarity positive voltage step to line P and line N. Then ground plane will be somewhere else. You have to have solid ground plane, otherwise it is gonna generate a huge amount of EMI. And this could be metal, and it has to be connected to the receiver and termination ground. Also, this metal ground has to be connected to the source ground. If you do not have this metal ground, return current has to go through somewhere else, and that will be a big EMI problem. So in order to transmit common mode with the speed of light, you have to have secure metal ground plane. In the case of differential signaling scheme, you remember that we're gonna have virtual ground plane between the two metals. But in this case, because we are exciting the common mode with the same polarity at line P and line N, we have to have a solid ground plane underneath. Also, I'm assuming that RC source termination is even mode impedance, and the receiver termination is designed with the even mode impedance. Then even mode reflection coefficient is becoming 0, and even mode reflection coefficient is becoming so. There will be no reflections, and there will be no reflection at the driving end. So we can avoid multiple reflections. You remember that usually even mode impedance is larger than 50 ohm if you are not properly design your interconnection. If the reflection coefficient is becoming negative number. So in order to avoid these multiple reflections, this termination should be terminated with even mode impedance, and source impedance should be terminated with the even mode impedance. That should be carefully designed. Then voltage wave, actually that is propagating along the line and the same polarity with the speed of light. That voltage wave will be determined by ohmic ratio between even mode source impedance and even mode source impedance and even mode source impedance and even mode impedance and even mode impedance. And if you are matching the source impedance and the even mode impedance, you're gonna have half voltage, and that will propagate along the coupled transmission line. In this case, current will be induced at the top metal, and opposite current will be induced at the metal ground plane. At the adjacent metal, we also generate the common mode, and same amount of common mode current will be induced at the metal ground plane. That current wave will be determined by the voltage step, common mode voltage step divided by even mode impedance. This is a short summary of a common mode excitation. Hwang Chan-young students, are you there? Happen to be there?
네, 교수님.
Your page, would you summarize this page for us?
네, 알겠습니다. 네, 디퍼런셜 앞전에 설명해 주셨던 디퍼런셜 모드와 다르게 이번 커먼 모드에서는 세임 폴라리티를 가진 스텝 펑션의 시그널이 들어올 경우를 가정합니다. 그럴 경우에 그 소스 임피던스가 이분 모드 임피던스로 매칭되고, 그 다음에 리시버 단의 터미네이션도 이분 모드 임피던스로 매칭됩니다. 그 경우에 네, 2번, 3번과 마찬가지로 네, 델타 V 웨이브가 2분의 V로 똑같이 같은 값으로 라이징하게 됩니다.
네, 맞습니다. 그래서 황찬호 학생하고 조금 대화를 한다면 하여튼
네.
이 커먼 모드, 디퍼런셜 모드 같은 경우 라인과 라인 사이에 버추얼 플레인이 생기는데, 이 경우는 별도의 그라운드 플레인으로 리턴 커런트가 돌아온다고 말씀을 드리겠습니다.
아, 네.
예, 그러니까 익사이테이션도 좀 다르고 임피던스도 다르고 전파 속도도 다르고 터미네이션도 달라요. 디퍼런셜 모드와 커먼 모드가.
네.
그러니까 두 개를 동시에 컨트롤을 해야 원하는 파형을 얻을 수 있다, 이렇게 말씀을 드리고, 만약에 어떤 경우에 한 라인에는 가만두고 한 라인만 펄스를 보내면 결론부터 얘기하면 이분과 오드 모드가 동시에 발생을 해요. 지금은 이제 나눠서 이렇게 슈퍼포지션으로 나눠서 해석을 했는데, 실제로는 그게 디퍼런셜 모드와 커먼 모드가 동시에 막 발생하고 전파되고 반사가 일어나기 때문에 조금 더 복잡한 현상이 있습니다. 제일 좋은 거는 커먼 모드는 아예 생기지 않게 하고 디퍼런셜 모드만 하면 제일 좋습니다. 그런데 하여튼 그 인터커넥션 라인 1과 라인 2 사이의 밸런스가 깨지면 커먼 모드가 생기기도 합니다. 네.
네, 감사합니다.
고맙습니다. In time, if we look at excitation of common mode, in the time mode, both line 1 and line 2 will have same step at time t equals 0, but at certain time delay, it will reach to the receiver and it will fill the step, and both line N and P line will have same voltage waveform. Because there is no reflections, there will be no ringing sense. So we're gonna have very clear step. And please remember that we're gonna have even mode time delay, and odd mode time delay is like, let's assume 550 picosecond is gonna be usually 1000 picosecond. So differential mode or common mode will be arriving at the receiver, or it will be short later. So this is using the time domain graph, I was trying to show the excitation and propagation of common mode. Now, let's move on to a new subject, saying that termination design. As I mentioned in the previous slides, I told you that we have to design both common mode and differential mode. And that means we also have to control the reflections of both common and differential and common mode. That means we're gonna have two different type of termination. One is differential mode, and another termination is common mode. And in this slide, I'm going to give you some cases of termination. First, I would like to start with pi termination. Pi termination has different, because we have to meet two different termination, differential and common mode. Basically, we need two termination resistors, R1 and R2. By combining R1 and R2, we can match odd mode impedance and even mode impedance. Let's start with discuss about odd mode termination, that is a differential mode termination. Because we have virtual ground plane, so wave will arrive with the speed of light, and the impedance from top metal to virtual ground plane is odd mode. Then termination is a parallel connection of R1 and R2. So this odd mode wave will fill termination with R1, R2 in parallel. That is R1 multiplied R2 divided by R1 plus R2. That is parallel effective impedance, and that should be matched to GOO, odd mode impedance. So in other words, if you are using pi termination, actually it is using two different resistance, R1 and R2. R1 is the connecting resistance between two differential line, and R2 is connecting line 1 to the virtual ground plane, and at the same time line R2 is connected to virtual ground plane. You remember that in this specific analysis, I'm assuming that this resistor is connected to ground, but in some case, this R2 can be connected to power. Sometimes this is connected to power. And then we can control the common mode reference voltage level above ground. In this case, I think a reference ground plane, common mode frame voltage will be the ground, 0 voltage level. But sometimes you want to bring up to a certain level, then this R2 has to be connected to power. Later on, I'm going to show you that examples. So if we want to avoid any of odd mode reflection, odd mode, to become 0, we have to make R1 and R2 parallel connection should be odd mode impedance. Why this odd mode impedance equation is simplified? Because we are assuming shunt resistor to R1, and half of them is R1 and half of them is R1, and we are in the middle. We are assuming that is connected to virtual ground. Now let's think about odd mode propagation case. We want to make even mode case. We want to make it 0 to avoid any reflection of common mode. And then you remember that this voltage level at line 1 and voltage level line 2 is equal to 0. So there will be no current between line 1 and line 2. So we can assume that we have open circuit in the middle of the two lines. In the differential mode termination, we are assuming that we have ground between the two lines. But in odd mode, even mode case, because we have same voltage level and there's no current between the two lines, in the middle, we are assuming this plane is open circuit, open circuit. Then if we are sending even mode, they are not feeling any current by R1. So totally this impedance is R2. I think this is a mistake. This is R2. So in order to avoid or remove any reflection of even mode, R2 should be matched to even mode impedance. By having this relationship 1 and 2, we have equation 1 and equation 2, we can obtain this total waveform, total equation. What does this mean? I would say that if you are using a pi type of termination, and if you want to remove any reflections of differential mode and common mode, you can determine the shunt series resistance R2 and series resistance R1 by using this equation. And for example, let's assume that even mode impedance is 55 ohm and odd mode is 45 ohm. By using this equation with these numbers, we can determine R2 as 55 ohm, R1 248 ohm. Let me summarize this slide. So if we have two wires over the ground, and we can excite differential mode and common mode separately, or sometimes we are combining them together to achieve certain waveforms. And in our case, if you want to remove any reflections of both differential mode and common mode, you can use this pi termination and you can use this relationship. And when I'm inducing this relationship, I used such the virtual ground plane and open circuit type of concept. Student 김경묵, are you still there?
네, 교수님, 있습니다.
Very nice to meet you. Good morning. Would you shortly summarize this slide, termination of coupled transmission line to us?
네. 혹시 틀리면 말씀해 주시면은,
네.
터미네이션을 파이 터미네이션으로 구성했을 때에 대한 강의시고, 터미네이션 라인에 션트 저항을 달아서, 오픈 터미네이션과, 이븐 터미네이션과 오드 터미네이션을 구성했을 때입니다. 그래서 오드 터미네이션을 구성했을 때는, 버추얼 그라운드가 생기면서 거기로 R1 저항이 R1과 R2가 패러럴하게 연결되어 있는 것처럼 구성되게 돼서 임피던스가 병렬 저항 임피던스로 계산이 되고, 그리고 이븐 모드에서는 버추얼 그라운드가 없기 때문에 R1 저항이 오픈 서킷으로 구성돼서 이때는 산식이 조금 더 복잡해지는, 산식이 R2만 보이게 되는 임피던스를 갖게 됩니다.
네.
그래서 결론적으로는 R1과 R2에 대한 공식은 이렇게 구할 수 있다라고 말씀을 해주셨습니다.
제 메시지는 하여튼 3메탈 시스템은 모두가 두 개가 존재하다는 거예요. 그래서 두 개 다 컨트롤 해야 된다. 그러니까 조금 복잡하죠. 그 컨트롤하는 것 중에 Excitation, Propagation, Deflection이 있는데, 이렇게 Deflection 입장에서 봤을 때 이렇게 두 개의 저항을 조합해서 두 개의 모드를 다 반사를 줄일 수 있다. 이런 예를 보여드렸습니다. 근데 거듭 말씀드리지만 이 디퍼런셜 시그널링의 풀 테이크 어드밴티지 하려면 디퍼런셜 모드만 존재해야 되고 커먼 모드는 존재하지 않아야 된다. 커먼 모드는 DC 레벨로만 존재하는 게 제일 좋다. 이 말씀을 드립니다. 그러니까 일반적으로는 디퍼런셜 모드 임피던스만 맞추죠. 오드 모드 라인 임피던스를 하고 터미네이션 하고 이렇게 맞추게 되겠습니다. 이 터미네이션은 그라운드에 붙을 수도 있고 파워에 붙을 수도 있습니다. 파워에 붙을 때는 레퍼런스 볼테이지 커먼 모드 레벨이 더 높아지겠죠. 그죠? 그런 게 하나가 있고, 근데 이제 파워가 붙을 때 조심해야 되는 거 하나는 파워 서킷이 임피던스가 제로여야 된다는 거죠. 그래야 그걸 이제 펄스 입장에서 봤을 때 그라운드로 보이기 때문에 그렇고요. 소스에서도 드라이빙 할 때 버추얼 그라운드하고 실제 그라운드가 잘 로우 임피던스로 연결이 돼야 됩니다. 근데 그게 잘 안 되는 거죠. 그래서 그라운드 설계가 훨씬 더 어렵다라고 말씀을 드릴 수 있겠습니다. Now let's move on the other type of case. Another type of termination is shunt termination. In this case, we are using just one resistance. That means when we are having odd mode wave is coming, and if R1 is matched to odd mode impedance, R1 is matched to odd mode impedance, we are not going, odd mode reflection coefficient is becoming zero. That's good. But if we are sending even mode wave, then this is open circuit that is disconnected. This is actually becoming open circuit termination. So even mode will be 100% reflected. So in the previous terminations, we are using two resistance, and that will be a little bit complicated, and it will produce more cost. Or in the chip area, it may be more, it will take more layout area, and also this resistance is depending on temperature and process, and so there is a lot of complicated issues. If there is any voltage difference between line 1 and line 2, there will be a DC current path. But there might be some disadvantages associated with pi terminations. For the simplicity, if you choose a single resistor and you connect two wires with 100 ohm, and let's assume that you have 50 ohm odd mode impedance, then odd mode reflection coefficient is becoming zero. That is good to minimize multiple reflections. But the penalty is that it is becoming open circuit terminations for odd mode excitation, and the reflection will be, common mode reflection will be 100%. And so that is the penalty coming from these shunt terminations. 재호, are you there? 김재호?
네, 교수님. 안녕하세요.
Would you shortly explain this slide for us?
네. 앞에 파이 모델의 경우에서 그 두 메탈의 끝에 R2가 이렇게 달려 있는데, 이 저항이 서로 미스매치가 있거나 이제 레이아웃에서 크기 문제도 있기 때문에 아예
네.
없애버리는 션트 션트 구조를 사용하게 됩니다. 근데 이렇게 되면은 장점이 오드 모드에서는 리플렉션이 아예 없어지게 되지만 단점은 이븐 모드에서는 이제 100% 리플렉션이 일어나기 때문에 이제 이런 단점이 있게 됩니다.
네, 훌륭합니다. 제가 영어도 잘 못하지만 이 강의 영어, 특히 수학과 그림이 많이 들어가는 영어는 참 어렵다는 생각이 좀 들더라고요. 쭉 흘러가는 게 아니라 이것과 저렇고 저렇고. 근데 제 강의보다 학생들 이해도가 더 좋은 것 같아요. 그래서 제가 요즘 드는 생각이, 제가 대학교 다닐 때 대학교 교수님들 강의에서 별로 배울 게 없었어요. 그 당시에는. 그래서 사실 혼자 공부를 많이 했거든요. 그런 게 또 단점도 되지만 장점이 스스로 공부하는 그 힘이 됐는데, 오늘 제 강의도 잘 못하지만 학생들이 이렇게 잘 듣는 거 보니까 그런 또 플러스 요소도 있는 것 같습니다. Now, let's think about another possible case of parallel termination. In the previous slide, termination is connected between a line 1 and line 2. Now, in this case, we have virtual ground plane and virtual ground plane. Termination R2 is connected to virtual ground plane. Then let's see what happens. In this case, R2 is terminated with the odd mode impedance and termination impedance is becoming 0. That's good. But for the case of even mode, I'm a little bit confused. Then even mode impedance reflection coefficient. So R2 is okay. This is my point. Okay, let's assume odd mode impedance is 50 ohm and termination is 50 ohm. Okay, then impedance is very well matched. But you remember that odd mode, even mode impedance is slightly larger than odd mode impedance. So let's assume that this even mode impedance is 55 ohm. Then because of mismatch of even mode and odd mode, there will be some reflections. 자, 무슨 말이냐면 even mode 임피던스는 55ohm이고 여기에 50ohm, 터미네이션이 55ohm이면 오드 모드는 반사 계수가 제로인데 even mode 웨이브가 오면 터미네이션 값이 작게 보이기 때문에 반사가 일어난다 이 말이겠습니다. In the previous case of shunt termination, the even mode is 100% reflected, but in parallel termination with one resistor, odd mode impedance is well matched, but some of even mode will be reflected. That is the point of parallel termination. Another possible termination method is T termination. In T termination, we have shunt resistor R2 and shunt resistor R1 and R1. And the middle of this shunt resistor, we are connecting R2. And then here also even mode case, we can with virtual ground plane, we can calculate termination condition. And overall even mode termination case, we are assuming we are having no current between the middle of two wires, then R2 can be split and we can calculate even mode termination condition. By combining this equation 1 and 2, we can obtain this equation. very 심플하게 말씀드리면 뭐 이분과 오드 모드가 있고 이분 조건의 virtual ground plane, 오드 모드에는 중간에 오픈 서킷, 태블린 디어리, 서킷 디어리를 해버리면 나누면 이 저항이 반반씩 나눠지기 때문에 양쪽 입장에서 반반씩 나누기 때문에 저항이 ER2가 돼갖고 이분 모드 임피던스 매칭 조건은 이게 되고 오드 모드 제거는 이렇게 된다. 그래서 the conclusion of this section of lecture is that to control the reflection of both differential mode and common mode, we have to match. We may need two resistors and R1 and R2. Depending on pi termination or T terminations, we may have different equations to determine R1 and R2. But sometimes to make simplicity, we can use the parallel termination or shunt termination. Comparing the shunt termination and parallel termination, probably parallel termination has a little bit of advantage. And in parallel termination case, we have very good odd mode matching, but in the case of even mode, we may have some 10% deflections. 여기까지가 또 다른 이제 서머리가 되겠습니다. 그래서 강의 앞부분에서 excitation 얘기했고요. 여기까지는 이제 termination 얘기를 했습니다. Now, I would like to talk about practical interconnections using the differential signaling scheme. One of them is serial ATA. Serial ATA. For example, when you are connecting your hard drive of your computer to your computer, we are using connections. In the long time ago, or maybe 10 or 20 years ago, if you have hard disk and if you have PC, you are using the ribbon cables. It's a very flat, but many I/O interconnection, number of interconnection might be 16 or 32. But in order to send high-speed signals, you have to have wires, but you have to have ground plane underneath. Then this cable will become very rigid. It is not flexible. Also, there is another issue associated with the skew. The length of this line is not the same. So arriving time of signal at the computer will not be the same. So I think over 100 megabps, I think this is not a feasible solution anymore. Another problem related to this ribbon cable is that it will disrupt airflow inside your computer. So that means your CPU temperature will become even higher and higher. In order to reduce the temperature increase in your PC, you have to make airflow using the air fan. But this ribbon cable is really problem for airflow. So because of that, we are moving into a serial interconnection. In the serial interconnection, we are using single differential pairs, but we are sending digital data very high speed, like 110 gigabps or 100 gigabps. By having these serial connections, we can reduce the size of cable. But disadvantage is that you need the serializer or deserializer. You have to have serializer circuit and deserialized circuit. But a big advantage of this is that you may have very thin single transmission line cable. So your system size will be very small, and you can enhance the airflow inside your computer. The connection solution between a hard disk and PCB in storage, especially in storage system, now we are using serial ATA system, and that's why we have serial. In order to send very high speed over 10 gigabps signal, and as I mentioned many times, we have to use the differential signaling scheme in order to maintain the impedance and to minimize EMI at the same time. This is a interconnection scheme of that serial ATA. First, we're gonna have odd mode impedance is 50 ohm and differential mode impedance is 100 ohm. By adjusting the width and space and thickness and dielectric constant in a coupled transmission line, you can achieve 100 ohm differential line impedance. In order to minimize the reflections, in order to avoid any reflection, termination impedance is 50 ohm, 50 ohm. We are using single termination. That means if we happen to have any common mode excitation, it will suffer multiple reflections. But in this specific case, they are assuming that they are not having any common mode and they are matching the termination with 50 ohm that is matched to odd mode impedance. At the transmitter side, they have also 50 ohm termination impedance, 50 ohm, that is matched to odd mode impedance. That means that reflection coefficient at the receiver and reflection coefficient at the source is both, and reflection coefficient is becoming 0. Another interesting thing is that at the transmitter side, they have source current. And that source current is 10 milliamps. So constant, in the driving side, you have to have a constant voltage source that the amount of current should be 10 milliamps. It is actually DC current. And it will control the amount of voltage wave and current wave and common mode levels. How are we going to generate common mode? We have to use the switching S2 and S1. They are simultaneously switching on and switch off. If there is any time skew between switching S2 and S1, it will create common mode. Later, maybe next Monday class, I'm going to talk about those skew issues. But we are assuming at this moment that the switching of S21, switching on and off of S21 and S1 should be simultaneous. That is very difficult part of I/O circuit design. But at this moment, I'm assuming that we have ideal switch S2 and S1, and they are turning on and off simultaneously. Now let's start to analyze DC analysis first. Let's assume that we switch S2 is on, then S1 is off. Then this 10 milliamps current will be conducted through or line 2 with termination resistor. And so 5 milliamps current will be conducted through or line 2, and 5 milliamps current will be conducted through a shunt resistor. So in this serial ATA, to have both differential mode and constant common mode, we are having penalty of 5 milliamps current is conducted to 50 ohm, and another 5 milliohm is conducted through the termination resistor. This will create the power consumption. Penalty of this interconnection scheme is that we are consuming a lot of power because of this common mode constant current 10 milliamps and 2 resistance connection. And because of this, and so higher voltage level line is the 250 millivolts. However, when the switch is off state, and this point is connected to ground, and this point is connected to ground. So off state voltage level is 0. So by switching S1 and S2, voltage level will go from 0 to 250 level, 250 level to 0 level, and that will switch. So amount of this total level 1 and level 2, and low level and high level will be 250 ohm, 250 millivolt. That is basically determined by this current source 10 milliamps and resistance of shunt source resistance and receiver shunt resistance, series resistance. Then what I can say is that high level is addition of even mode and odd mode by superposition principle. Low level is even mode minus odd mode. That means common mode level is 125 millivolt and odd mode voltage is 125 millivolt and minus odd mode voltage of 125 millivolt. So source current and termination scheme to avoid any deflections of differential mode. By combining this and the power supply, we have even mode voltage. Actually, this is common mode and reference voltage is becoming 125 millivolt, and odd mode voltage is 125 millivolt. In the previous slides of excitation analysis, I am assuming just delta V, but in real implementations, by having this termination impedance, and let's assume that if you have higher current source, you're gonna have a larger odd mode differential mode voltage. But the penalty of that is you're gonna consume more power. Let's assume you can reduce this to 5 milliamps, then we can reduce the power consumption, but penalty is coming from the reduced odd mode voltage. If you have reduced odd mode voltage, then at the receiver side, you're gonna have smaller voltage margin to determine a digital level high or low. That is very difficult job. And also, you can calculate on current and off current. Always 5 milliamps will be conducted through source termination, and 5 milliamps will be conducted either through line 1 or line 2. So on line current is 5 milliohms because source already 5 milliohms is consumed at the source side, and the off current is open circuit, so 0 milliohm. So what we see here is that even mode and odd mode addition is the 5 milliohms, and even mode and odd mode difference, that is off current, is 0 milliohm. That means even mode current is 2.5 milliohm. Actually, this is wave current, and the odd mode wave current is 2.5 milliohms. And if voltage division of odd mode and even mode is becoming 50 ohm, 125 millivolt divided by 2.5 milliamps, that is becoming odd mode impedance. So DC analysis and wave analysis is exactly well matched in this special case. As I mentioned in the previous slide, we have common mode reference level that is 125 millivolt. Odd mode wave voltage is 125 millivolt, and minus odd mode voltage 125 millivolt. We have common mode current 5 milliamps, and odd mode current is 2.5 milliamps, and odd mode current is 2.5 milliamps. And current is 5 milliamp, okay. And differential mode impedance is this 200, differential line-to-line voltage is 250 millivolt, and current is 2.5 milliamps. So because of that, we have 100 ohm differential mode impedance, that is twice of odd mode impedance. So in case of serial ATA, once again, I would like to emphasize that reference voltage level, common mode is 120 millivolts. Logically, higher voltage level is 250 millivolt, and logically low level is 0 millivolt. Actually, at the receiver hand, this is the logically high level and this is low level. In terms of wave propagation, odd mode propagation will propagate with 125 millivolts, and negative 125 millivolt odd mode wave will propagate along the ground plane. And please remember that this common mode level is actually virtual ground plane. Jeho, are you still there?
네, 교수님.
한번 설명해 봐 주실래요? 앞에 오늘 강의에서 excitation, 뭐 propagation, reflection 얘기했는데 여기는 실제 문제로 한번 들어가서 지시 해석과 웨이브 해석을 막 섞어서 해봤습니다. 한번 설명 부탁드립니다.
네, 일단 처음에 이 페이지에서 교수님께서 왜 이 시리얼 ATA를 사용하게 되었는지부터 설명을 해주셨는데,
네,
그 전에 사용하던 그 리본 케이블의 경우에 이 라인 케이블의 길이가 모두 다르기 때문에
네,
그 PC에 도착하는 시간이 달라 스큐에 문제가 있었고, 그리고
그렇습니다.
또 리본 케이블은 이제 PC 안에 온도를 엄청나게 올려버리기 때문에
네,
이제 시리얼로 설계를 시작하게 되었습니다. 그런데 이제 이렇게 시리얼로 하게 되면 케이블을 줄일 수 있지만 뭐 시리얼라이저나 디시리얼라이저 서킷이 들어가게 되고, 그런데 이제 이렇게 얇은 트랜스미션 라인을 쓰기 때문에 온도 측면에서도 좋고 거리적으로도 좋다고 이제 배웠습니다.
네,
그리고
맞습니다.
이제 본격적으로 이 회로에 대해서 이제 보면 스위치가 이제 S1, S2가 있는데 이 두 스위치가 이제 컴플리멘터리하게 S1이 꺼지면 S2가 바로 켜지는 그런 식으로 구성이 되어 있는데, 만약에 이게 제대로 뭐 컴플리멘터리 되지 않게 되면 커먼 모드에서 문제가 발생하게 되지만 일단 수업 시간에는 그 컴플리멘터리하게 켜지고 꺼지게 설정을 해 두었습니다. 그래서 이제 소스 커런트의 경우에는 10mA가 있고, 이제 만약에 S2가 켜지게 되면 이 모든 전류가 50ohm으로 왼쪽으로도 가고 이제 오른쪽 그 터미네이션 쪽으로도 가게 되는데,
네,
그렇게 되면 이제 페널티가 그 컨스턴트한 파워가 계속 소모가 되고,
그렇습니다.
네, 그리고 이제 만약에 이 소스 커런트를 크게 해주면 이 하이 볼티지가 커지기 때문에 그 볼티지 마진이 좀 커서 쉽게 구분할 수 있지만, 이제 단점은 그 많은 파워가 소비된다는 단점이 있고, 그리고 뭐 이븐 모드 볼티지나 오드 모드 볼티지가 이렇게 125mA 갖게 되고, 이븐 모드 커런트, 오드 모드 커런트 모두 2.5mA로 갖게 되는 것을 확인할 수 있었습니다.
네.
네.
네, 맞습니다. 그래가지고 만약에 오실로스코프로 파형을 찍어본다면 오른쪽 같이 찍어지는 거예요. 수신다에서 라인 1과 라인 2를 찍으면. 예. 그래서 그 파형을 볼 때 DC적으로 보면 온 볼테이지, 오프 볼테이지, 온 커런트, 오프 커런트인데, 웨이브적으로 보면 커먼 모드가 중간을 흐르고 오드 모드가 반반씩 이렇게 되게 돼서 그 웨이브로 계산한 임피던스와 또 회로적으로 계산한 임피던스가 또 맞아 떨어지게 됩니다. 네, 고맙습니다. 그리고 혹시 이게 제가 시리얼 ATA로 지금 설명을 했는데 이거 말고 또 이 시리얼로 시그널링 하는 게 케이블링에서도 어떤 게 있을까요? 혹시 기억이 나나요? 김재호님?
네, 다시 한 번만.
예.
네.
그래서 이 시리얼 ATA 말고 디퍼런셜 시그널링 스킴 쓰는 게 어떤 게 있는지 혹시 생각나는 게 있나요?
그것까지는 잘 모르겠어요. 네.
USB. USB 볼 때 보면 이렇게 꼽는데 그 안을 들어보면 메탈이 4개가 이렇게 들어가 있어요.
네, 맞습니다.
패턴이 이렇게. 요게 이제 디퍼런셜 PN이고 1번, 2번이고 요 옆에 게 하나가 파워고 하나가 그라운드예요.
네.
그래서 요 파워는 웨이브적으로 보면 그라운드와 같고, 그래서 요 두 개가 연결돼 있기 때문에 이제 우리는 이제 그라운드가 밑에 있는 게 아니라 옆에 있으면서 포메탈 시스템이 이게 사실 서로 연결돼 있어서 그 안에 두 개가 디퍼런셜로 시그널링 합니다.
감사합니다.
예, 그래서 요 버추얼 그라운드 플레인이 중간에 이게 연결이 되는 거죠. 근데 이제 아래 기판을 못 넣고 하여튼 4개가 컨택이 이루어지도록 그렇게 만들었죠. 그죠? 근데 USB 하나는 P를 쓰는 이유가 파워도 공급해야 되기 때문에 그런 아이디어를 낸 것 같아요. 근데 이제 AC, 웨이브적으로 보면 P나 그라운드나 다 메탈이기 때문에 그냥 메탈이 양쪽에 있구나. 그래서 커먼 모드는 양쪽으로 흐릅니다. 그 다음에 혹시 HDMI라고 기억나시나요?
네, 교수님.
예, HDMI도 블루, 레드, 그린, 클락 4개의 시그널을 보내는데 시리얼로 못 보내니까 디퍼런셜 4페어를 통해서 이렇게 보냅니다. 그렇게 되면 셋탑박스나 테레비 사이의 케이블이 벌키해지지 않고 간단하게 되니까, 그래서 여러분 기억하실지 모르겠지만 아주 옛날에 10년 전에 PC에서 빔 프로젝트 연결하려면 BGA 케이블인가 뭐 이상한 거 썼었어요. 그게 다 패럴 커넥션에서 다 시리얼 커넥션으로 가는 게 인터커넥션 숫자를 줄이려고. 예. 그 다음에 컴퓨터와 컴퓨터 사이는 이제 PCI 익스프레스를 씁니다. 그리고 지금 GPU와 CPU와 DRAM 사이는 아직은 패럴을 쓰는데 바이 16, 바이 32 그것도 언젠가 시리얼로 바뀌지 않겠나, 디퍼런셜로. 근데 이제 코스트가 인터커넥션 숫자가 너무 커지니까 그런 2배가 되니까 그런 게 있고, 파워 소모가 이게 너무 크잖아요. 그죠? 일반적인 우리 SSTR 지난 시간에 한 거는 그냥 오픈 터미네이션이라 DC 파워 소모가 되게 DC 파워가 소모. 그러니까 이 파워 소모를 줄이려니까 소스 커런트 10mA를 줄일 수밖에 없거든요. 그러면 리시버의 마진이 줄어들어요. 타이밍과 볼테이지 마진이. 그러니까 외부의 노이즈에 너무 민감하니까 또 EMI가 중요해지고 시그널 인테그리티가 중요해져. 그러니까 인터커넥션을 시리얼라이즈 해야죠. 그 다음에 파워 소모도 줄여야죠. 노이즈도 줄여야죠. 이런 그 중심에 이제 시그널 인테그리티가 있습니다. 김재현 학생 오늘 고맙습니다.
네, 감사합니다, 교수님.
네, 다음 시간에는 더 나아가서 조금 이런 시리얼 ATA 말고 조금 다른 스킴도 한번 여러분들 소개해 드리고요. 원리는 다 비슷합니다. 그 다음에는 커먼 모드와 디퍼런셜 모드를 어떻게 아까 지금까지는 커먼 모드는 커먼 모드만 있고 디퍼런셜만 디퍼런셜 모드가 있다고 그랬는데 이게 둘 사이에 왔다 갔다 해요. 디퍼런셜 모드가 갑자기 커먼 모드로 바뀌기도 하고 이런 컨버전 문제 하나 하고, 그 다음에 디퍼런셜 모드가 생기지 않도록 하려면 어떻게 해야 되냐, 이 얘기를 좀 해보려고 합니다. 여기서 아까 스위칭이 S1, S2가 뭐 PMOS 트랜지스터나 NMOS 트랜지스터인데 그거 다 파라스틱이 있고 인터커넥션이 있고 컨트롤 로직에서 실수가 있으면 다 스큐가 생길 수 있거든요. 그러면 이제 커먼 모드가 생깁니다. 이런 문제를 한번 얘기해 보겠습니다. 오늘 여러분 경청해 주셔서 감사하고요. 제가 강의하는 거에 비해서 여러분 설명 보니까 더 찰떡같이 알아듣는 것 같습니다. 여러분 훌륭하십니다. 오늘 강의 여기까지 마치고 다음에 뵙겠습니다. 수고하셨습니다.